Now, what is the meaning of analogous systems? Okay. Meaning. Now, the two systems are said to be analogous if they share similar, okay, if they share similar mathematical model. Okay. Now, if the two systems, okay, have the similar mathematical model, then the systems can be called as analogous system. Okay. Now, with this analogous system, understanding, one can convert a mechanical system into electrical system. Okay. Or an electrical system can be converted into a mechanical system. By doing which, electrical engineer, okay, or electronics engineer can understand mechanical systems very easily. The same case holds good with the vice versa approach also. Okay, that's because in the end, you try to write down the mathematical equation of a physical model. Okay, once the equations are in place, then we will be able to carry out computer-based simulations. Okay, so that's the reason, electrical engineers, they try to visualize a mechanical system in electrical domain, whereas the mechanical engineer can try to visualize an electrical system into a mechanical domain. Okay, so that is possible with an analogy called as analogous system network analogy. So this is for linear, or you could say translational system. Okay, and the second one is for rotational system. Okay. So this analogous systems can be broadly classified into two types. Okay, rotational system analogy and translational system analogy. F stands for force, V stands for voltage. Similarly, T stands for torque, and V stands for voltage. Okay, in a similar manner, okay, instead of voltage, okay, you can have the current source in electrical system. So accordingly, okay, you can also have force current analogy, which is called as Fi analogy. Similarly, you can also have torque current analogy. Okay, so F remains forcing function. Okay, that is the linear forcing function. I stands for current. Similarly, T stands for torque and I stands for current. Okay, so in translational systems, totally you can have two types of analogy: force voltage analogy and force current analogy. Similarly, in case of rotational system, you can have torque voltage analogy or torque current analogy. Okay, so first let us try to understand the force voltage analogy. Here the objective is to compare a mechanical system with an electrical system. Okay, with an electrical system. Okay, now after comparing, okay, we try to list out the similar elements. In the sense, in case of translational system, the fundamental elements are mass, spring, and damper, right? In case of electrical system, if at all you consider the KVL way, you will have the voltage as the forcing function, Then you have resistors, inductors, and capacitors. On the other hand, if you consider KCL-based systems, your forcing function going to be a current source, right? And then you have the passive elements, resistors, inductors, and capacitors. So basically, we are trying to, find out the similar components from electrical systems and its respective counterparts in mechanical system. Okay. Now, let us consider a simple 3-element translational system. Okay. Say suppose the system is something of this kind. Okay. So we are considering a 3-element translational system. Okay, this is your reference frame, the spring element, the frictional element, and the mass element. Okay. Let's say this is the direction of external force, and in the direction of external force, you're going to have the linear displacement. Okay, as you know that mass element will have only one displacement. On the other hand, element K and B can have two displacements, provided we are allowing both the terminals to move freely or not. But in the given example, you can see that one of the terminal of K as well as terminal of P is rigidly fixed to a reference frame. Hence, K and B will have only one displacement, and the given displacement is x of t. Okay, so let us write down its equivalent mechanical system. Okay, other day we have seen, right? Equivalent mechanical system will have a node which is x of t, and then it will also have a reference frame. Okay, your mass element, frictional element, and the spring element, and the force function. Okay, then let us write down the differential equation. Okay, we have f of t is equal to m into x double dot of t, that is d square x by dt square, and then we have b into x single dot of t, and then we have k into x of t. Okay, let us find its Laplace transformation. F of t becomes f of s. This becomes s square m into x of s plus sb into x of s plus k into x of s. Okay. Now let us consider this as equation 1. Okay. We have already written this particular equation in the previous class. Okay. Now, this is the mathematical equation you are going to get for a 3-element translational system. Okay. Now, what we will do, consider a 3-element electrical system. Okay. Now, so that means to say series RLC circuit. Series RLC circuit. Okay. So the forcing function is the voltage. Okay, and then you have resistor, inductor, and a capacitor. Now this is your loop current I of t. Okay, so let us apply KVL. So what do you get when you apply KVL? Applied voltage V of t is equal to voltage across the inductor, voltage plus voltage across the resistor, plus voltage across the capacitor. So basically it is VR plus VL plus VC, or V of t is equal to R into I of t plus L into di of t divided by dt plus 1 by C into integration I of t into dt. Okay, so this is in the time domain. You have kept this equation in time domain. We will convert it into Laplace domain. So V of t is V of s, R into I of s, plus Ls into I of s, plus 1 by Cs into I of s. Okay, so this is your equation 2. Okay, now compare equation 1 with equation 2. Okay, when you compare equation 1 with equation 2, you get some similar terms, but the degree of equation 2 is not similar to that of equation 1. That means to say, your equation 1 is having s square term, right? So the highest power of s in equation 1 is 2. On the other hand, the highest power of s in equation 2 is 1. So you cannot compare equation 1 with equation 2 because the two degrees are different. So what you have to do is, with a meaningful substitution, you are supposed to bring equation 2's degree to 2. Now, how do we do that? So what we can do is we can use the definition of current. Okay, so current is defined as rate of flow of charge, right? So I is equal to dq by dt, right? So the Laplace transformation becomes, okay, what I will do, let me show the time dependency also. So I can write current as I of t. Okay, so what I'm going to do, the current I'm going to replace with some meaningful substitution. So I of t is equal to dq of t divided by dt. Or in Laplace domain, I can write I of t as I of s, which is equal to, it's a differential function. So you get s into q of s. Okay. Or q of s is equal to I of s by s. So that means to say charge is nothing but integration of current. Okay, it simply says that charge is nothing but integration of current. Okay. Now what you can do is you can substitute in place of current the charge. Okay, let's say this is equation 3. Okay. Then you write substitute equation 3 in equation 2. Okay, let's see what will happen. So when we do that, we get V of s is equal to R into I of s. Okay, but what is I of s? I of s is s into q of s, plus you have Ls into I of s. I of s is s into q of s, plus 1 by Cs into s into q of s. Okay, so this s gets cancelled, and you will get V of s is equal to here Ls into s. So this becomes s square into L into q of s, plus you have s to the power 1. So this becomes s into R into q of s, plus independent of s, right? So 1 by C into q of s. And let us consider this as equation 4. Okay, and let us highlight this particular equation. Okay. Now you compare equation 1 and equation 4. Okay. Now you look at equation 1 and just a little I'll minimize. Yeah, you look at equation 1. The highest power of S in equation 1 is 2. And in equation 4, the highest power of S in equation 4 is also 2. Now you can say that the two systems are analogous. That means to say they share identical mathematical model, right? The highest power of S is 2 in both the equations. And then you have power of S as 1. And then you have a term which is independent of S. So that means to say it's a proper second order equation. Okay. Now you can start comparing the coefficients. Okay. In the sense, the variable, okay, the variable in equation 1 is what? X of S. On the other hand, the variable in equation 4 is Q of S. Okay, so the counterpart of displacement in electrical system is charge. Okay, so you can write here X counterpart is Q. Okay, let's see. Let's start comparing the other coefficients. Okay. Now, what is the coefficient of S square? In equation 1, the coefficient of S square is the mass term, right? Similarly, the coefficient of S square in equation 4 is the inductance. So the counterpart of mass in electrical system is the inductance. So I can write EM's counterpart is L. Okay, so on and so forth. So similarly, you can look at the coefficient of S to the power 1 in equation 1. What is it? It is friction B. On the other hand, in electrical system, the coefficient of S to the power 1 is resistance R. So counterpart of friction is resistance. Okay. Similarly, the counterpart of spring constant is reciprocal of capacitance. Okay. So this is called as, okay. Finally, what is the counterpart of force? What is the counterpart of force? You have F in mechanical system and you have V in electrical system, right? So counterpart of force is the voltage. So that's the reason it is called as force voltage analogy. F-V analogy. Okay. So on one side, you have mechanical elements, including the variables. Okay, and on the other side, you have electrical elements. Okay, so in future, when we deal with analogous systems based on FV analogy, what we try to do is that we will try to replace all the mechanical elements with its counterparts. Okay, that means to say, if at all we see any displacement, we are going to replace that displacement with charge Q. And if in case, if you encounter any mass element, you are going to replace that particular mass element with inductance L. So this is called as force voltage analogy. Okay. Is it clear how to determine the counterparts of electrical and mechanical systems?
Yes, sir.
Okay, fine. Fine. So now let us look at the force current analogy. Okay. Fi analogy. Okay. Now, for Fi analogy, okay, the mathematical equation for the mechanical system remains the same, right? Because we are not going to change the forcing function. The forcing function is still f of t. So let me just rewrite. So for the mechanical system, okay, let me write directly in Laplace domain because we have already written the description. F of s is equal to what? S square m into x of s plus sb into x of s plus k into x of s. Okay, let us consider this as equation 1. Okay. Now let us consider electrical system. Okay. Since you're talking about current, so let us consider electrical system on the basis of current as the forcing function. Okay, current as the forcing function. Okay. Now, what kind of circuit you are going to use? You have to use 3-element electrical network because in mechanical system you have the 3 elements as mass, dashpot, and spring. So over here we are going to use a parallel RLC circuit. Okay. So for current analogy, we are going to consider a parallel RLC circuit. Okay. So let us assume that the node voltage, the node value is V of t. Okay. In case of parallel RLC circuit, all the elements are connected between node V of t and ground, right? Okay. Let's say this is the resistive element, and let's say this is the inductive element, and let's say this is the capacitive element. This is C, this is R, and this is L, and this is the current. I of t. Okay. So as per KCL, the supplied current I of t is equal to sum of the element currents. Okay, IL of t plus IR of t plus IC of t. So as per KCL, the input current I of t is equal to IL of t plus IR of t plus IC of t. Okay, if you recollect, I have written the current relations for an inductor, for an capacitor, and also for a resistor, right? Somewhere in class number 5, I think. Okay, you can just go back and you can just see. Okay, now I of t is equal to, okay, what is current through the resistor? Ohm's law, right? V by R. So IR of t is nothing but VR of t divided by R. So voltage by resistance gives the resistive current. Okay. Plus, what about the capacitor? Okay. What about the capacitor? In case of capacitor current. Okay. The capacitor current is nothing but the rate of change of voltage, right? C times D. Sorry, I shouldn't have used this R subscript because the node voltage I have taken as V. So it is simply V of t. So current through the capacitor is nothing but C times dV of t divided by dt. So rate of change of voltage. Okay. And current through the inductor is nothing but 1 by L into integration of voltage, V of t into dt. Okay. Or the Laplace counterpart, I of t as I of s. V of t becomes V of s divided by R plus C into, it's a differential function, so S into V of s plus, it's an integral function, so you will have 1 by L into 1 by S or 1 by Ls into V of s. Okay. Let's take this as equation 2. Okay. Now here the same problem exists, right? If you compare equation 1 with equation 2, you see that there is order mismatch. In the sense, equation 1 is a second order system. On the other hand, equation 2 looks like it's a first order system. So the degrees are not the same, hence you cannot compare equation 1 with equation 2, provided you bring in some valid manipulation to convert equation 2 into a second order system. Okay. Now, since the order of equation 2 is not equal to the order of equation 1, we will try to bring the order of equation 2 to a second order one. Okay. So to do that, what we will do is, let us use the definition of voltage. Definition of voltage from Faraday's law. From Faraday's law. That means to say, V of t is equal to d phi of t divided by dt. Okay. So rate of change of, the voltage induced is directly proportional to rate of change of flux. Okay. Or V of s is equal to, in Laplace domain, V of s is equal to, it is d phi by dt. So it's a differential function. So you get s into phi of s. Okay. So take this as equation 3. Okay. Substitute equation 3 in equation 2. Okay. So what do we get? I of s is equal to, okay, let me write the conductance part as 1 by r, okay, into V of s. So what do we have? V of s as s into phi of s. So let me write it, s into phi of s. Plus, let us write c as it is. And then we have s, and then we have vs, right? What is V of s? V of s is s into phi of s plus 1 by ls into V of s. That's again s into phi of s. So this s and this s gets cancelled. So you are left with I of s is equal to, here you are, s into s is s square. So s square into c into phi of s plus you have s to the power 1 over here. So it is s into the coefficient 1 by r into the variable phi of s plus you have a term which is independent of s, which is 1 by l into phi of s. Okay. So s square, s to the power 1 and s to the power 0. So this is your second order system. Okay. So this is your second order system. Let me put it in a box so that you'll be able to compare it. Okay. Now compare equation 1, right, with equation 4. So when you compare equation 1 with equation 4, okay, you can see that the highest power of s in equation 1 is s square, and the highest power of s in equation 4 is also s square. So the degree of equation 1 and equation 4 is 2. So both are second order equations. Hence, you can say that both the systems have the identical or the similar mathematical model. So when they have the similar mathematical model, okay, you will be able to carry out the analogy. Okay, let's do that. Now, the coefficient of highest power of S in mechanical system is M, right? On the other hand, the coefficient of S square in electrical system is C. Similarly, the coefficient of S to the power 1 in equation 1 is frictional coefficient B. On the other hand, in case of electrical system, the coefficient of S to the power 1 is conductance, or 1 by R. Okay. And finally, you can identify the coefficient of S to the power 0, which is expansion coefficient K. And in your electrical system, you have reciprocal of inductance, 1 by L. All right. So you can start listing the counterparts. So counterpart of M in electrical system is C. Counterpart of friction in electrical system is 1 by R. And counterpart of spring coefficient K in electrical system is reciprocal of inductance. Okay. And then you have the signal. Okay. In your mechanical system, the signal was the displacement, X of S. On the other hand, in your electrical system, the signal value is phi of S, or the flux, right? So in place of X, the linear displacement, you have the signal as flux phi. Okay. And finally, in place of force F, okay, what do you have? You have current I. So the counterpart of force is current. That's the reason it is called as Fi analogy. Okay. So this is your mech elements, and this is your electrical elements. Okay. And the corresponding analogy is called as Fi analogy. Okay. Did you understand this? Okay. Now, in a similar way, you can even carry out the analysis of rotational systems as well. Okay. So let me write down the subheading as analysis of rotational systems. Okay. So for rotational system, okay, you have to consider 3-element system, right? So the 3-element rotational system is nothing but K, B, and J. Okay, let's say this is the shaft, and this is the applied torque. Let's say we are applying the torque in clockwise direction. So the displacement, the angular displacement, will take place in the clockwise direction as well. Okay. And for this particular mechanical system, you can write down the time domain torque equation. So applied torque T of T is equal to torque consumed by the element J. So Tj of T plus the frictional element Tb of T plus the spring element Tk of T, or T of T is equal to J times theta double dot of T plus B times theta single dot of T plus K into theta of T. Okay. In Laplace domain, T of T is equal to T of S is equal to, it's a double differential function. So S square into J into theta of S plus single differential function. So SB into theta of S plus K into theta of S. Okay, so this is your mechanical system, mathematical model. Okay. Now, for torque voltage analogy, or TV analogy, let us consider electrical system as series RLC circuit. Series RLC circuit. All right. So what is that series RLC circuit? Forcing function V of T. Just now we have considered, right? Resistor R, inductor L, and capacitor C, and the current as I of T. Okay, I don't have to explain it once again. What we get is V of S is equal to R into I of S plus Ls into I of S plus 1 by Cs into I of S. And let us consider I of T as dq of T divided by dt, or in Laplace domain, this becomes I of S. Okay, I of S is equal to S into Q of S. Okay, so substitute I of S in place of, substitute I of S in equation 2. So V of S is equal to R into I of S. What is I of S? S into Q of S plus Ls remains as it is, and in place of I of S, you substitute S into Q of S plus 1 by Cs into S into Q of S. The same equation, what we discussed, okay, a couple of minutes back. So what is that electrical representation you are going to get? You are going to get electrical representation as V of S is equal to R into S into Q of S. Okay, sorry, let us put it in proper way. Highest power of S is S square, then L into Q of S. Okay, I'll take one more minute. Plus, highest power of S is S to the power 1. You will have to arrange basically in the descending powers of S. So S square first, then S to the power 1, followed by S to the power 0. So this is S into R into Q of S, and then 1 by C into Q of S. So this is your equation 3. Now you compare equation 1 and equation 3. Okay, you will have the counterparts of electrical systems, right? So you have force, right? So you have force in mechanical system. Sorry, not force, torque, right? Because it's a rotational system. So against torque, you have voltage. Against angular displacement, what do you have? You have charge. Okay, similarly, against mass, you have inductance. Against friction, you have resistance. And against expansion coefficient, you have reciprocal of capacitance. Okay, so basically, you will have a list of the counterparts of respective systems, right? So for torque, you have voltage, hence it is called as TV analogy. TV analogy, right? In the similar manner, you can also write TI analogy. Because the discussion is already being held, right? It's been already held, right? So what do you have? In TI analogy, against torque, you will have current in your electrical system. So this is your electrical system, and this is your mechanical system. And against theta, you will have flux. Against mass, you will have capacitance. Against friction, you will have reciprocal of resistance. And against expansion coefficient, you will have reciprocal of inductance. Okay, so this is TV analogy table, and this is TI analogy table. Okay, so in today's class, what we discussed is the analogous systems.